Okay, let me start my first paper presentation. Today I will introduce this paper, PaperSkimn, Learning to Classify Images Without Labels. It's published in ECCV 2020. This paper is from this group, from this university. Okay, let's talk a little about the background. There are several existing papers. The authors think they can those papers can be categorized. There are two categories. One is use the two-stage approach. They basically use at the first stage they use the representation learning method. For example, they can use the very host method, contrastive learning, in the first stage. Then they use in the second stage, because in the first stage they have learned good features. Then in second stage they use based on the fixed features, they apply the linear supervised learning or the clustering method, like the k-means method, to assign those features to different clusters. This is the first type. The second type is the end-to-end, purely unsupervised method. In those methods, there are two types. One is like the self-training. They are initialized by certain features, and then they iteratively get supervision signal from the most confident samples. Then it's self-labeling or self-training method, or they can do the reclustering method. Second type is the they will to learn. They will use a learnable clustering method function. This function may evolve a neural network, which this function can maximize the mutual information between the image and its neighbors, or some neighbors. So this is the end-to-end method, purely unsupervised, without any label information. So it's not like this one, this linear supervised learning. It's based on the features. So let's combine these two methods by treating them as because they have different components. So we treat them as a Lego. Then we combine to a new hammer. In this paper, they combine the authors. They combine the component into a new hammer to do the to improve the method. So let's talk a bit about it. That is so what we can see is that we have the first part, the feature learning or the representation learning, and we can see it also happened in the end-to-end approach. It's also based on some features. So this is the first component. We need the feature learning. So we extract it, and then for the two-stage method, they use linear supervised. It's not we won't use it because we don't use any labels in here. And the clustering means it's a fixed clustering, so it's not good enough. Then the authors they adopt this one, a learnable clustering function. And this self-training, they can also use it as a additional extra improvement. So now we have, so in this paper, they also consider a two-stage. One is use this one, the feature learning, representation learning, feature learning as the first stage. Then they use a learnable clustering function. Learnable clustering function. This function is based on this those features from the feature learning, and we can the authors think they can also add the self-training, self-labeling method to get further improvement. So we can see they just extract different components to improve the method. So the first stage about the feature representation learning. Basically, this paper they adopt the Sinclair method from Hinton, from the Hinton's group. So they use the Sinclair to do the training. Then they found that those learned features can find very good neighbors, very good similar instance. We can see this image. For the left column is the images, and the other columns are the neighbor samples to be the nearest neighbors. And we can see most case they have in most case they are the same category. But some case will make mistakes. And they also do some statistic analysis. If they choose different number of nearest neighbors, the correct percentage, they show the correct percentage. So we can see basically they can have a good for those data sets, they can have a very good accuracy. Then which means it's the feature learning, like the Sinclair contrastive learning, they can learn very good features. The second step, they based on the better learned feature from contrastive learning, they have found better neighbors, more accurate labels. Then the learned feature H should because it should be close to all of its neighbors by this function. It's called similarity of the H, the hidden features of xi, and it should close to the hidden features of xi's neighbors. So the similar function, we can choose different matrix. For example, the inner product with the W times X is W times X times cosine of the data, and the KL divergence, and also L2 distance, W subtract X. So it's in this paper they choose the inner product. It's okay. Then also we also have different choices to compute the similarity. One is directly use these features H. Also, we can also consider further. We can use the probability vector after an extra neural network. Then we get the H from the fixed features. Then we go through a new neural network GX G function. Then we pass it through the softmax. Then we know it will return us give us a probability vector. Then so the G function. It's related. It's based on a neural network. It can be learned. We can learn this neural network, and also we need the probability to regularize our final logic, final score. So in this paper, they adopt the probability vector to compute the similarity. So it's similarity between probability of the xi and the p of neighbor xi. So this term of it is right like this one. It's for every x, for every single image in the data set, they find k neighbors, and to compute the distance, compute the similarity between these two. Here they use this phi. I think it's phi. maybe I make some mistake, because this is a neural network and with the softmax. So this will return a probability vector, and this is another probability vector to take the inner product and take log. Then we hope these two probabilities, these two features should too close to each other, close enough. So when we optimize this value, this is the first term. But if we only consider this term, it will have a critical issue. That is, if we just make all of the images, we assign all of the images to a single cluster, to a single category, then it also the score's value can also be very good. It also get a very good value. So we need a regularization over the categories. We need to assign those, for example, 60,000 images to 10 categories. So it requires a regularization, which means we need to make those images assigned to different categories with a uniform distribution. So the average probability vector over all images, because each image will have a probability vector like 0.1, 0.2, 0.7. Then we took some of them, then take the average of. It should like a uniform distribution. So this is the goal to do the regularization. But how to make it? Yeah, use the entropy. The entropy, we know it can compute like this one. If it's a very confident probability, the entropy will be 0. If it's really confusing case, for example, the 10 classes, all of them have the probability 0.1, then the final entropy is the log 10. I'm not sure the value, but obviously this one is larger than this one, so we want to make the entropy we want to maximize. We also want to maximize the entropy to make the to solve this critical issue. We want the different images can assign to different cluster, so we want to maximize the entropy. But in the optimize the loss function, we need, because for optimization we want to make the value, for example, we want to get a larger value. To optimize it, we should take a negative. So it's -10. So finally we to then take a negative and make it smaller and smaller. And this is the I have talked about the first two stages, and further improvement from the self-labeling, self-training, because most confident samples, their predicted probability on some category, on some classes, on a category can be very close to 1%, 100% confident. So, so in this case, those samples, because they are very confident, so we can give the pseudocode, a pseudo label. If they have the category, for example, it's like the cat is 1, the dog is 0, the shark is 0, then the pseudocode will assign this cat. But it's a general case. It should work in most cases, but sometimes, we know the some adversarial examples can fool the neural network, so it's not always hold. And also the calibration, the research on the calibration issue also mentioned that some neural network can be overconfident. But in most cases, the pseudocode can improve the performance. Then we combine the two stages. It's called the MiningNearest Neighbors, because we first get the features. We get the first fixed features, and then we compute the. We want to minimize the distance to the neighbors for every single images in the data set. Then we also take the optimize the entropy over all data sets to assign the images to different categories. So this one is, we can see it's take x from all data sets and to compute the probability vector, and took this sum and divide, which means it's the average over all the probability over the overall probability vector. So the algorithm, given the data set and the neural networks and some clusters task, we'll go through it. We optimize with the task. It's the cluster, like the contrastive learning. Optimize the first one. Then we, based on this one, we go to select the k neighbors of this of xi, and go to update this phi eta with the scan loss. It's this one is the contrastive learning. This one is the learnable softmax function to find the to do the clustering. And okay, yeah. Okay, this is the clustering step, the equation with this equation to update the softmax function, because they have learned the phi of data of the contrastive learning. Then this one is to optimize the softmax function. And then finally, they use the self-labeling step to, if the probability larger than a threshold, they use the cross entropy with the given y, or with the pseudo label y. Then they also update the softmax function, and finally finally they return this one. And this is the algorithm, and they have many experimental results. Basically, I don't like introduce the results. They have very good results. Sometimes this so many ablation studies, and this one without false positive. The images are false other categories, but the cluster predicted positive. So if they remove those results, those images, it will be the upper bound of this one. This one, the right figure is the upper bound of the left figure. And we can see for some case, we can also select zero neighbors, and after select 5 neighbors, it almost achieve the best performance. And we can compare directly compare the scan with the supervised results. It's very, I think it has a very good result. Maybe this one is not good enough. But the scan without any labels is better than the k-means. The learnable softmax function is better than the k-means. They also tried on ImageNet with 200 classes. It also have a very big improvement. And compare with the semi-supervised learning method, they can also, with 1% label data on ImageNet, they can also have very good performance comparable to the Sinclair and the CPC v2. But this paper, they don't need any labels. So in a summary, they combine different components together. This paper based on the contrastive learning or feature learning. They use the better learning method to learn better fixed features. Then and they found those learned features can find better neighbors, more accurate neighbors. Then they replace the k-means for contrastive learning method. Use the NN-based neural networks-based learnable clustering function. It means given a fixed feature, they go through a neural network and then go through the softmax to get the probability vector. Then they use the probability vector with another probability vector from its neighbor to compute the similarity and maximize the similarity between the X and its neighbors. The first, because they need to prevent this collapsing into a single category issue, they use the entropy as a regularization. And they also incorporate the self-labeling method. So further work, I think people may consider how to create the general end-to-end framework other than the two-stage, because now it's two-stage. They need first learn the better. They need to first use the contrastive learning, then fix the features. It's not a end-to-end framework. Okay, thank you. Well, Chinese. Yeah, forgot to write in English. Stop it. Thank you.